Okay, so I'm going to very briefly go over the top part of the recipe card. The bottom of the recipe card is essentially the same as what we've had before, so I don't see substantial need. The very first thing we need to do is write the hypothesis, and the null will always be equal every single time. But this time we have two separate means, two independent means. So it's mean one equals mean two. And the alternative is either going to be not equal, less than, or greater than. And then we need to make sure we define mu1 and mu2. Now, that's the part that people don't like. We're going to have to define mu1 and mu2 for both. So let mu1 equal, let mu2 equal. Then we get to write our conditions. Both samples are random. That's nothing new. N is less than 10% of the population. Populations are independent of each other. I probably should write that, of each other. And we need a normal population, or N has greater than 30. Now, the bad news is we get to do conditions for both sets of data. We get to do conditions for mu1 and mu2. So you have double the conditions. The same ones, but you get to do it twice. Our equation has changed, and it looks initially scary, but it's not. Because initially we had t equals x bar minus mu s divided by the square root of n. Well, this is essentially the same thing. Because I could have written this as t equals x bar minus mu s squared divided by n, like that. But we have two sets of data. So basically I have x bar 1 and x bar 2. So this part's essentially the same. And that's where that comes from, okay? All right, other than that, we probably need to move on and start writing, carrying out a hypothesis test, because there's not substantial differences in the problems. So the average ACT scores on an independent random sample of 16 non-athletes at Blinn College. By the way, they said simple random sample. That's good. Was compared to an independent random sample of 7 athletes. The school's guidance counselor was curious to know whether or not Blinn was admitting athletes with lower ACT scores than non-athletes perform an appropriate test to state your conclusion. Well, as I said, mu1 equals mu2. That's always going to be the case. This will, for two samples, this will always be the case. And obviously I have two sets of data, so it's either going to be paired or two sample. Well, the data links are different, so that means it can't be paired. But beyond that, I have two independent groups. I have athletes versus non-athletes. So since I have two independent groups, that also means it's going to be a two sample. So this is going to be a two sample test. Mu1 equal to true population mean ACT score of non-athletes. Mu2, the true population mean ACT score of athletes. Because that's what we're comparing, ACT scores of non-athletes versus that of athletes. And as I said, we get to do the conditions twice. Random sample, well, they gave it to us. 16 divided by 0.1 is 160. It's reasonable to assume that there are at least 160 students at Blinn who are not athletes or who are non-athletes. Compare that over here. Random sample was given. 7 divided by 0.1 is 70. Reasonable to assume that there are at least 70 students at Blinn who are, and by the way, this should say not, this should not have said not, this should have said athletes. The samples are independent, that was a given. But they didn't, but the bad news is they did not tell me the populations were normal. And our sample sizes were 16 and 7, so we can't say they're normal by central limit theorem. So I need to go ahead and graph these things. So I hope this shows up because I'm not using my normal calculator for this. So I've gone ahead and gone to stat edit and I've entered the data. See if I can't help that out just a little bit. No, that didn't help very much. Let's see. That makes it worse. Sorry, guys. Trying to make this show up a little better. That's about as good as it's going to get. Okay, so I'm going to stat, edit, and I entered the data into L1 and L2. Then I go to second stat plot, press enter, make sure the first one is on. My data is in L1, so second one. And then I'm going to go ahead and go up to stat plot 2, press enter, arrow to the left, press enter. Select the appropriate box plot. Now this data is in L2. And if I've done everything correctly, which I'm not sure I have, by the way, this happens often. If you just go ahead and press clear, that'll take care of the problem and go zoom 9. I get 2 distinct box plots. All right. I go to the trace feature, and it gives me my lower value is 19. And by the way, the top one is the one in L1. Just notice how it says L1, and this one is in L2. And so I can go ahead and draw those individual box plots. All right, and I need to draw them on separate scales. And so this should have said, been labeled athletes, ACT, excuse me, non-athletes, and this should be athletes, ACT. And you don't have to draw a scale. You can actually just sit there and label the high points if you want to. Now, both box plots appear to be reasonably symmetric with no outliers. The distribution appears to be approximately normal. So in that case, we're good to go. So we need to go ahead and run our test. And it's better off if you just run your test and then come back and record your information. You'll see why in just a second. So we have my equation, which I've written, t equals x bar 1 minus x bar 2, s1 squared divided by n1 plus s2 squared divided by n2. This will come to in just a moment. It's going to come from the calculator. Okay. So I'm going to go stat, test, and I'm going to drop down to looks like number 4, which is 2 sample t-test. And I have data. And my data is in L1 and L2. Our frequency is 1 for both of them. And my inequality that I had for my alternative hypothesis was a greater than. So I'm going to use a greater than. And by the way, this thing asks about pooling. We will never pool. We will never pool. So this is always going to be a no each and every time. And we end up getting T 2.02. So the probability that T is greater than 2.021 equals 0.0352. And there's our degrees of freedom. Now, the reason I didn't go over the degrees of freedom, we just copied from the calculator. It's a very complicated formula. Not that you couldn't do it, but you don't have to. They'll accept it straight off the calculator. So just go ahead and write it down. But you must, you must write this down, okay? Now, as I scroll down, we have 24.75 is X1. We also have X2 is 21.86, S1 2.84, S2 3.287, so 3.29. Sample size N1 is 16, N2 is 17, and make sure you plug those into your formula. All right, so very important that you make this list and make this list and plug it in. All right, and if you have data, I would go ahead and run the formula, run the equation just as we did, and then plug it in. We got a p-value of 0.0352. They didn't, and they told us alpha 0.05. So this is less than. Because it's less than, we're rejecting the null. So what are we saying? Our p-value is 0.0352. We reject the null. There's sufficient evidence at alpha equal 0.05 to suggest that the difference in the true population mean of ACT scores for non-athletes is greater than that of athletes. On average, non-athletes have a higher ACT score than athletes. And this is the simplified, not always want you to start doing this. From this point on, always give a simplified. Just really straightforward, nothing long, nothing fancy, on average. And by the way, because we're talking about means, on average, non-athletes have higher ACT scores than athletes, because that's our general consensus. All right, so that's the one on hypothesis test. The next one we will do will be on confidence intervals.